Okay, and let's see if my new toy works. I'm easily pleased. Okay, so I know last week we looked at the applying finite difference approximations to solving a simple PDE, but that was kind of that was sort of rushing ahead of ourselves a wee bit. That PDE we solved was a hyperbolic one, which is actually the hardest type of PDE to solve. We're going to be looking today and next week at solving elliptic PDEs. Can anybody recall what an elliptic PDE was? What's different about it? Without reading on that page 33 of the notes. Okay, elliptic PDEs model what we call steady state problems. Steady state problems means it doesn't matter what's happening to the time, the solution's always going to be the same. Okay, so i.e. the solution is a steady state. So the solutions to an elliptic PDE do not evolve over time. Once you have the solution, that's it. Not going to change unless you change something about the system. Unless you may change the boundary conditions, or you may change the actual PDE itself. Okay, so they're steady state. They do not change over time. So therefore, the independent variables are just the spatial coordinates: x and y if we're in 2 dimensions, x, y, z if we're in 3. Okay. Notice that t is normally an independent variable. Okay, but in this case, because it doesn't change with time, we just remove it. Solution. Okay, look at that. No, I'm easily pleased to tell you. Solutions are smooth with no discontinuities. Discontinuities means a sudden abrupt change in the profile of the solution. So solutions are going to be nice, smooth surfaces. Okay, we'll come on to look at hyperbolic PDEs in a few weeks, which do have abrupt changes in their solutions, which can cause our numerical methods a bit of difficulty. But for elliptic PDEs, they're smooth, no discontinuities. Okay, essentially there are 2 examples of elliptic PDE. Well, actually there's many more, but these are the 2 you'll see. So you've met this one before, the Poisson equation. Okay, so remember u is a function. That's what our solution is. Okay, so the partial differential equation is partial derivatives in terms of that function u. So that's what you always got to remember. We're trying to find what u is. We don't know what u is, but we do know what the partial derivatives of u combined be. Okay, so the second order partial derivative of u with respect to x plus the second order with respect to y, that equals 0. That's the Poisson's equation. Okay, Poisson's equation, very, very similar. Stick a function on the end. Function of x and y, that could be a constant. So whereas that's 0, that could be a constant, that could be a number, or it could be any sort of function of x and y. And these are used to model sort of gravitational, electrical, magnetic fields, that sort of thing. Oops. Yeah, what's happening there? Okay, so that's what we're going to be looking at both today and next week, looking at the solution of mainly the Poisson's equation. Okay, so last week we looked at a one-dimensional domain. So remember we had that line. Okay, we had like an x sort of arrow, an x line going through, and what we did, we put our finite difference points at various positions along that line. That was a 1D domain. So we refer to that as a 1D solution. 2D solution, okay, so here we've got the x domain, okay, which is horizontal, and we've also got this y domain, which is vertical. Okay, so we have a 2-dimensional domain. This sort of confuses quite a lot of times. We have arguments with the engineers. Okay, so what we're going to have is when we have a solution, if we plot the solution to this, it gives us a 3-dimensional surface. So the engineers say to us, "Oh, well, that's a 3D solution." No, it's a 2D solution because the domain is 2D. It just happens to have some values above it. We're always having arguments with engineers about that sort of thing. We're right, they're wrong. They're probably having the same sort of thing in their lectures about that. There we go. Okay, so this is a 2-dimensional domain. So here I've got a simplified version. So it's just a rectangle. And in the same way as last week, where we had a 1-dimensional line with loads of finite difference nodes on it, this time we're going to put our finite difference nodes on our two-dimensional domain. So notice, there's a couple of things I want you to notice here. We have a uniform distribution. That means the distances between each node is the same throughout the domain. Okay. That doesn't always have to be the case. Okay, you can have them different. It does make your solver, does make your numerical method slightly trickier. But that can be done, but in this case, they're uniform. And also, they're in this sort of grid formation. Okay, so we can't have them sort of all over the place. We need to have them in this grid formation. Okay, so all of these sort of black dots here, those are my finite difference nodes. Okay, so the spacing along the x direction, I'm going to refer to the distance between nodes in the x direction as delta x, and in the y direction is delta y. Delta x and delta y don't have to be the same. In the x direction and the y direction if you want to. It does make it easier if they're the same, but they don't have to be. And essentially what we're doing is we are calculating the solution at this point, or at these points. Okay. In sort of, to be absolutely correct, if we had a PDE which applies over this whole domain, there'd be an infinite number of points for which we should be able to say, okay, that's a value. But we're simplifying it. And we can't do an infinite number of points, so we take a finite number of points and solve just at those points. Okay, it's called an Eulerian method. Okay, so that's discretizing the 2D domain. So similar to what we saw last week, if you've got the length of your domain in the x and y directions, and you know how many nodes you want to put into our domain, you can calculate your delta x and delta y. Just a slight little notation thing here. I've used uppercase x and y to denote the number of nodes in the x and y directions, just so it doesn't look like they're partial derivatives. So if you're wondering why those are uppercase, it's just so they're not confused. Partial derivatives. Okay, so I'll go back a slide. I'll go back a slide. Oh, that didn't take long, did it? Right. If I go back a slide, okay, you can see the x domain starts at A. Oh, what's working again? Starts at A and ends at B. Okay, so therefore, in the x direction, distance between the nodes is just b minus a divided by number of nodes. Now in this case, if I say nx plus 1, because you've always got that plus 1 when you're at each end. So in this case, I've chosen how many have I? 1, 2, 3, 4, 5, 6, 7. So I've got 7 nodes across there. Okay, so my nx would be 6. So I'm saying, okay, the plus 1. Sometimes we use the plus 1, sometimes we don't. So delta x is b minus a over nx. So in that case, nx was 6. So whatever b and a are, divided by 6, and we get our delta x. So very, very similar to delta y. Once we've got delta x and delta y, you can also calculate the coordinates of each node. Now, the x coordinate, because we had that structured grid system, okay, we only need one sort of array of x coordinates. Okay, so the smallest x value plus I times delta x, where I is that index, that'll give us our x coordinates. Okay, so x, this I'm going to explain about I and j in a minute. Okay, so this is our x coordinates, and that's our y coordinates. Okay, so that's discretizing our domain. Okay, and I mentioned about I and j. Okay, this is sort of something which it's quite easy to get a bit confused at. Last week I looked at the idea of subscript notation. So rather than saying x plus delta x all the time or x plus 2 delta x, we used I. So I plus 1 is one step to the right, I minus 1 is one step to the left. Okay, if we extend this idea to 2 dimensions, okay, so I'm, instead of, as well as I'm introducing that second index j. So we refer to I and j as indexes or indices. Okay. So I will tell us what's happening, what we're doing across the x direction. So if we start at the one in the middle, which is uij, if I go ui minus 1j, that tells me I'm stepping 1 to the left in the x direction. And if I step one to the right, I have u I plus 1j. Now the j, I goes left to right, j goes up and down. So the ij plus 1 means we step once up in terms of the y direction, and ij minus 1 down in the y direction. So I and j these are the indices. I goes horizontal, j goes vertical. Now this is where it starts to get a bit tricky. If you're dealing with matrices, it's the other way around. When we're dealing with indexes and matrices, we normally go I going down, j going across. But always stick with one, or pick one and stick to it. Okay, so it can be difficult, especially when you start to program, when you start getting the indices sort of mixed up. This seems to be the sort of the preferred method in the literature, so that's why I'm sticking with it. So just remember, if you're doing something in MATLAB with all this stuff, remember it's sort of like the other way around. That makes sense. So with matrix indexing, the first number gives you the row, so you're going down, and the second number gives you the column, so you're going across. With this node indexing, the first number goes across, and the second number goes up. That's something to bear in mind there. Okay, and again, we have the width in the x direction is delta x, and the distance in the y direction is delta y. So, because we've got a 2D domain, we have to have two indexes. If we had a 1D domain, we wouldn't bother with j, we just have i's. Okay, I mentioned a little bit about this last week, but it sort of brushed over a wee bit, and this is the idea of boundary conditions. Now, last week we looked at using, it was a backwards difference for the space derivative. And what a backwards difference needs, it needs a node to the left of where you are to actually calculate the next value. But what if you're on the edge of the domain? So, for example, if this node here, if this required a value from outside the domain to calculate it, it can't because there's nothing there. Okay, so what we do is we tend to set, well, there are a couple of different ways in which we're going to treat boundary conditions. But one of the easiest ways to do it is to say, okay, any node which falls exactly on the boundary, we're going to remove from our calculation. And we're not going to bother trying to calculate that one. Instead, the value of that node is going to be specified by some boundary condition. Some condition which is placed on the value of this node, which is sort of not really, it may be relevant for the solution, but sometimes it is, sometimes it isn't. And we also do the same at the other end. Okay, so the zero node is on the boundary, the nth node is also on the boundary. The easiest way, or one of the easiest ways in which we can treat these is we solve for u1 up to un minus 1. So all the ones in between we solve for, we don't solve for those. And there are two types of boundary conditions. There are Dirichlet boundary conditions and Neumann boundary conditions, not von Neumann. So Dirichlet boundary conditions, these are the easiest ones. We basically just set a value for the edge. Let's say you were sort of modeling something heating up, and you know that one edge is always going to be at 0 degrees. So therefore, you use a Dirichlet boundary condition because you always know that temperature at the edge is going to be 0. Okay, values of the boundary can be constant, so you can set them to be 0, you can set them to be a number, however you want it, or they can adhere to some function. So we could have a function of x, y, and t. Okay, so depending on where they are in the domain or what their position is, boundary condition may be the same. If we didn't have an elliptic equation, let's say we had a parabolic or hyperbolic, where our solution would change over time. Okay, there may be a function of time. So, for example, and this is quite a common example, if you're modeling water and you want to introduce a wave, okay, the height of the boundary will change like a sinusoidal. So you just make the height of one boundary go up and down in terms of time, and that affects your solution. Another neat one you can do is have your boundaries modeling periodic behavior. This is what I like to refer to as Pac-Man boundary condition. You ever played Pac-Man? Showing my age here again, but Pac-Man, they've got a couple of little sort of corridors on either side of the maze. Okay, he goes out of one corridor and he comes straight back in, sort of like the other end of the screen. That's exactly what happens here. So what we do is we sort of leap around. So this left-hand boundary value, that assumes the same value as the sort of last computational node. Okay, and this one assumes the same value as the first computational node. So if I had something happening over here, this, by applying this boundary condition, this node here thinks it's up here. Okay, so let's say something was flowing out that way, will it appear right back in this way, and vice versa. Okay, it's a way we can make what we call quasi-infinite long domains. If you wanted an infinitely long sort of tube or something like that, you can use periodic boundaries. Okay, so that's the easier one of the two methods, just to set whatever your node value is to either a constant, some function, or periodic. Okay, the second one is a Neumann boundary condition. Now this is when you set the boundary node to be equal to some derivative. Okay, and this means whatever's going on in the domain will affect what goes on at the boundary. Okay, so for example, let's say you're modeling water and you've got a big wave coming to one boundary. That the wave approaching that boundary will affect the value of the boundary node. Okay, so the values of the boundary nodes are determined by evaluating derivatives. And these are just derivatives we've set. And what we also do is we sort of cheat a bit. We introduce what's called ghost nodes. So these are like fake nodes that don't really exist. Okay, so ghost nodes, we introduce them at any boundary which we use the Neumann boundary conditions at. So if I assume that this node is just outside of my left boundary, I've given it the number -1. That means I can now calculate the value of this node here. And the same at the other end. The reason why we include this ghost node is so that now I've got this information and I know what this is, I can calculate the gradient across that boundary. And that's quite useful. A couple of reasons why it's quite useful. Let's say I had a wave, I'm modeling water, a wave's coming towards one boundary, and let's say I want it to pass out of the boundary without any sort of obstruction. If I set the gradient to be 0, that's going to happen. Also, I might want the wave coming towards this boundary and then reflecting off of it, crashing against, like as if it was a wall, and then reflecting back. I can also do that with derivatives. So in Neumann boundary conditions, we have some gradient or some derivative across the boundary. Okay, so let's say our derivative is some function ux equals some function u. Okay, and it's a first order derivative, so let's use the central difference formula from our finite difference toolkit. Okay, so if I was to take ux at the 0 node, I take the value of u1 minus the value of u minus 1 divided by 2 lots of the step length. That's what we got here. So u1 is the bound value to the left of u0, u minus 1 is the value to the right of u0 divided by 2 lots of step length. Okay, and then whatever that function is here. Okay, rearrange it to make the ghost node the subject. Okay, and that's the value of the ghost node. And you can see it's dependent upon that node u1, its step length, delta x, and whatever that function is. Usually that function is 0. Okay. So for example, if we wanted what we call a transmissive boundary, that's when something that flows out of a boundary just flows as if it wasn't there, just sort of disappears, then this function here would be 0, and therefore we just have the ghost node would equal to u1. Very, very simple application, and likewise at the other end. That's if you've got transmissive boundaries. That's a very common boundary condition. If you've got some PDE which has velocity as its as one of its dependent variables to specify a solid boundary where nothing can escape from it. What we do is we set the value of the velocity at the ghost node to be negative the value of the velocity in the interior node. Essentially, that's like having a mirror. Think of a mirror being at the boundary. Anything that's happening within the boundary is sort of being mirrored the other side. So if you've got a wave approaching the left boundary, you've got an equivalent wave approaching the right one. Okay, so don't really worry about Neumann boundary conditions for now. Okay, we're just going to be looking at Dirichlet ones. Okie dokie, right, so we've discretized our domain. Okay, in this case, we're going to look at 2D because we've got a 2D PDE. We've learned about boundary conditions, so now we're going to solve, or we're going to derive a scheme to solve the Laplace's equation. Okay, so what we need is we need a way to approximate the second order derivative, partial derivative with respect to x, and the second order with respect to y. If we go to our finite difference toolkit, which we looked at last week, okay, we can take second order derivatives. Okay, so this is from the finite difference toolkit. This is a second order accurate approximation of that derivative there. So we replace that one with this. As you notice, this is in the x direction, so the j's stay the same. They're not being altered. It's only the i's that are changing all over the step length in the x direction. And we do the same for the y derivative. Okay. In this case, notice the i's are staying the same. They're not changing. It's the j's that are changing. And what we want is we want this node here. We want to calculate an expression for the value of this node, uij. And we've got minus 2 lots of it there. And we've also got minus 2 lots of it there. So I'm going to have to do a bit of algebra. Okay, so if we rearrange to make it the subject, after a couple of lines, it's not too difficult, we get this expression here. Okay, notice all of these are neighbouring nodes. This is a node which I want to solve for. These are all neighbours of it. Okay. If delta x and delta y are the same, this simplifies to this. Okay, so it simplifies actually quite significantly. All we have is you just add up. That's a node above it, to the top. That's a node to the right. That's a node beneath it. And that's a node to the left. So you just go top, right, bottom, left, add them all up, divide by 4, you get the solution. So in effect, using a second order finite difference approximation gives, all you have to do is find the average of the nodes to the top, bottom, left, and right, and we can solve the node ij. But of course, that is going to affect its neighbouring nodes. Okay, so we have to solve for all nodes across the domain. Okay, so there's a stencil. That's the node you're solving for, and it requires the values from those nodes there. And it's very common to actually use compass notation, north, east, south, west. Okay, so O means the one in the middle, north, east, south, west, add them all up, divide by 4. That's only, add them all up, divide by 4 is only when delta x and delta y are the same. If they're different, you can't make that simplification. Right, so we're going to have a look at an example. This is a very reduced domain, by the way. Okay, so if you see here, we've got some x, we've got a 2D domain. I've got 5 nodes in total along the x direction. I've got 4 nodes in the y direction. Okay. In this case, the delta x and delta y are the same, even though there's a different number of nodes. The domain isn't as large in the y direction as it is in the x. This is a very few number of nodes. Normally we'd have thousands of nodes or millions. Okay, so obviously for purposes of example, I'll just cut it down a bit. Okay, notice the ij notation. So the one in the bottom left, I is 0 and j is 0. Okay, if I go 1 across, okay, I add 1 to y. If I go 1 up, I add 1 to j, etc. So the first node, the first number is sort of going across. The second number is going up. And I think this is something I sort of omitted from the notes. It's in there somewhere, maybe in a couple of pages' time. The one thing I didn't specify was the boundary conditions in this example. Okay, so in this case, with all of the boundary nodes, we're going to use Dirichlet boundary conditions, and these are set of these numbers. These numbers aren't special, I just picked them off the top of my head. I don't think there's anything special about them. So for the boundary nodes, we have, they're always going to be constant. So that node will always be 7.2. The nodes in grey, that's what we're going to solve for. Okay, so now we've only got 6 nodes in total to solve for. Okay, so what we're going to do is I'm going to apply that finite difference scheme to this domain. So to start with node 1, 1. Okay, essentially it's north, east, south, west, add them all up. But if you notice, the one to the south and the one to the west, we actually know what the value is. So we add them all up and divide by 4. Okay. I'm using what we call row by column order here, so I'm going to go across the next one on the row. Okay, do the same thing. In this case, we have 3 computational nodes here. And we have the just the one boundary node. Keep going across. Okay, so we're in a corner again, so we've only got 2 computational nodes, and we've got the 2 boundary nodes. So we keep going. So we've gone across one row. So row by column order, so we go across a row, and once we finish that, we go up to the next row and do the same. So we're doing row by column order. Okay, so U1, 2. Okay, so here again, we're back to where we've got 2 boundary nodes to the top and to the left, and we've got 2 computational nodes to the right and to beneath. And we keep going. Okay, so after we've done that, we now have 6 expressions. So I've got 6 nodes, I have 6 expressions. And if you count the number of unknowns, we've also got 6 unknowns. It's an algebraic system, so a linear algebraic system. So we can solve this. So we have this system. Now, how did I get from the previous slide to this one? All I've done is I've taken all the unknowns and written on the left-hand side. So in other words, anything involving U, and any constant, i.e., for example, 6.8 and 7.2, I've just added them together. Okay. So all I've done is I've taken these 2 over the other side and left what we know on the right-hand side. So the unknowns are on the left, the knowns on the right. And we end up with this system. 6 equations, 6 unknowns, and you know from your work in the first year, linear system of equations, we can write it as a matrix equation. So here's our coefficient matrix. Here we have a vector of the nodes. Okay, so notice I've gone row by column. So node 1, 1, then I've gone across to node 2, 1, across to node 3, 1, then I've gone up to the next row. Okay, and then, so for example, the first equation is 4 times U1, 1, minus 1 times U2, 1, minus 1 times U1, 2. And that equals 14. Okay, so we have our matrix equation. We can solve those matrix equations quite easily, and everything's good. Apart from it isn't, because what you'll find is when you use thousands upon thousands of nodes, you'll have lots and lots of zeros in your coefficient matrix. It wastes energy. It wastes memory. Okay, and it's quite computationally inefficient to solve this using, for example, Gaussian elimination. The Gaussian elimination is okay for smaller systems, but when we're talking about thousands of nodes, it's far too computationally expensive. So what we do is we use a numerical method. Okay, and the class of numerical methods we're going to be using is called indirect. Okay, now you've seen direct methods before. You've seen Gaussian elimination. These are fine, but they're inefficient for large systems. Okay, we're going to be using an indirect method, and you may have seen these before. Jacobi last year, Gauss-Seidel. Okay. So Jacobi is an indirect method. Direct method means you go straight to the solution and you're done. Indirect method means you calculate a solution, but you can keep on improving on that solution. It's an estimate, and you keep on improving and improving until you think your estimate is good enough. Okay, so you start with an estimate solution, and you can repeatedly improve it until two successive estimates agree to some desired accuracy. Okay, and the notation we've used here is I'm going to have a superscript denote the current estimate. So superscript k says, okay, that's our current estimate. The superscript k plus 1 means, okay, what's the next improved estimate? Okay, and then all you do is, in the finite difference scheme we derived earlier, on the left-hand side, the node ij, you stick a superscript k plus 1 on. So that's going to say, okay, I'm going to improve this, the estimate of this node using the current k nodes. Okay, so if we're going back to our example, I'm using starting values of 0. Now remember, elliptic PDEs are steady state. Okay, they don't change over time. It doesn't matter what starting values I use. I could have used ridiculously big numbers, small numbers. Doesn't matter. You're going to get the solution in the end. So it really doesn't matter what starting values you use. We tend to use 0, it's pretty obvious. Okay, so if I look at this node here, node 1, 1. Okay, if I sum to north, east, south, and west, going around, a couple of them are zeros already, so that makes it a bit easier. Divide by 4, and I get my next estimate of that value is 3.5. So the original estimate was 0. My next estimate is 3.5. Okay, go across, and I'm doing similar. So here we are, go to north, east, south, and west. In this case, they're all zeros. It's just the one on the bottom which changes. Okay. And I go across again and do the same for all the other computational nodes. So now, after I've done all 6 of them, I have 6 estimates for my solution. Okay. It's not going to be very good because I started with zeros, unless the solution was close to 0. It's not really very good. But I have a better estimate. And then I can use these values in my next iteration. Okay, so doing the same thing again. Okay, notice the superscript has now gone up to 2, so that just shows, okay, we're in the second iteration of it now. Okay, so in this case, this is our estimate after the first iteration. Okay, so again, the north, east, south, west nodes, add them up, divide by 4, and get a next estimate. Okay, do the same for the other 6 computational nodes. Okay, and this should be an improvement. It's not always going to be an improvement. Sometimes the Jacobi method actually diverges, means it goes further away from the solution. Okay, in that case, you have to use some other method. But this should be an improvement over what we just had. And you keep going and keep going and keep going. So the more times you do this, if it converges, the better your solution. How do we know when to stop though? I mean, if we can keep doing one more, that solution is going to be better than the one we currently got. So you can keep going forever. So we need some form of what we call a convergence criteria. Now this is basically saying, okay, when do we stop? And essentially what they do is they continue until 2 successive iterations, or the difference between them, is less than some predefined accuracy. The problem we have here is we have 6 nodes, and in practice you'll have thousands. So in our example, we have 6 nodes. So how do we know? One node could be bang on. One node could have reached the solution, but we can't sort of assume that node's reached the solution when another node hasn't. So we need some measure of the difference between 2 iterations. Okay, and what a useful one to use, there's plenty you can use. I'm not saying this is the only one. Okay, it's the idea of a vector norm. Magnitude of a vector is an example of a vector norm. Okay, so if x is a vector, the 2 norm is what is also known as the magnitude. Simply square your values of your vector, add them all up, and find the square root, and that will give you your a single number, which is called the Euclidean norm. Okay, that's also known as the magnitude of a vector. And if your vector has just got two numbers, it's also known as Pythagoras. So it's the same thing. So if our best estimate minus the one previous to that is sufficiently small, then what we say is they're all approximately equal to the actual solution U. Okay. And we use this sort of convergence criteria. Tom is some small number. That's what you set. 10 to the minus 6 is a popular one. 10 to the minus 4 if you don't need it as accurate. Sometimes you don't need it as accurate. Sometimes you need it really accurate. If you're doing, for example, chemical kinetic problems, you're often dealing with very, very, very small numbers. So you might need that told to be very small. If you're dealing with something, a large system with large numbers, for example, astrophysics, that tolerance may be much larger. So it depends on what your application is. Okay, so we keep doing the iterations until the the norm between these two is less than that tolerance. Okay, so going back to R1, I'm not going to. This is a bit of a pain to do it by hand, to be honest. But here we have 6 nodes. So our starting values for all our nodes are 0, and these numbers here was our solution after one iteration. Okay, so find the difference between them, square them, add them all together, find their square root. We do that, we get 8.9757. Do the same for the iteration 1 and 2. Okay, so exactly the same, find their difference, square them, add them all together, find the square root, and we get 4.8745. Notice it doesn't matter which way around we're subtracting them because we're only going to square them afterwards. So doesn't matter. Okay. Point being is this number here is smaller than that number. And if I was to do it for a third iteration, it would be smaller still. Okay, so we can keep going until that becomes really small. Okay, there are actually a couple of different types of errors we can use. Well, there are quite a few, but the main sort of fall under one of these two. We've got the idea of an absolute error. Absolute error is just a norm of one estimate minus the other. It's called absolute because if these were just single values, this would be equal to the absolute value they're different. Okay, and the relative error is the it takes into account what are the size of our solution. So in this case, you do the absolute error, then you divide by the norm of your most recent iteration. So that's the difference between your last two iterations relative to the last iteration. When should you use one over the other? Well, here's a quick example. I'm going to calculate the absolute error between two values, 0.01 and 0.001. Okay, absolute one, it's very, very easy to calculate, you get 0.009. If I did the relative error, I get 9. Okay, so using absolute, I get a very small number for the error. Using the relative error, I get a very large one. What if I was to do similar to large numbers? And I think in your notes, I may have sort of not missed out that one, I think. Okay, so doing the same for quite large values of x. So one we've got 100,000, and the other we've got 100,100. The absolute error is 100, which you think was quite large. Relative error is tiny. Okay, so even though these are 100, the difference between these two is 100. Relatively speaking, it's small. So the choice of whether you use absolute error or relative error will totally depend on what numbers you have. If you've got small numbers, you might be better off using absolute error. If you've got large numbers, you might be better off using relative error. That's something you've got to decide upon. Okay, so this is the sort of procedure. Most sort of numerical methods start with the same type of procedure. You start with initializing your variables. What's the size of the domain? How many nodes have I got? Things like that. Calculate x. Well, that will be your x and y's, your coordinates of your nodes, and also set some initial value. Okay? you may be given the initial conditions. If you're not, I always tend to use zeros. As long as the error is less than the tolerance, sorry, the error is greater than tolerance, we update our estimate using whatever method you've got, then calculate the error, and then you update your values. Okay, and you keep doing those, sort of looping around until your error is less than tol, and then you know you're finished. It's very sort of similar. This is iterating until convergence. So we don't know when we're going to stop. Okay, so we have to use a while loop if we're coding this up in MATLAB. Okay, if I was to do that example, these are the solutions you get after a while. I think this is 10 to the minus 6 error. So those are the solutions. And using Jacobi, okay, that took 33 iterations. Not something I'd recommend doing by hand. Hopefully you're starting to see sort of the pattern in what I'm trying to say. Don't do things by hand, use the computer. Okay, so you can see those are our sort of first iteration values, second, etc. That's the I use the absolute error here, and you can see it goes smaller and smaller and smaller until after 33 iterations. This has probably been rounded up to 6 decimal places. Okay, that's Jacobi method. Right, just to finish off this part of the lecture, I'm going to explain a bit more about the lab sheet in a minute. But there's a worked example on page 51, so you might have to go forward a few pages. Okay, so what I thought I'd do is give you an example, just this sort of a slightly different example than what we've just done, so you can see the steps required. Here we've got Poisson's equation. Very, very similar to Laplace's, but we've got that extra function on the right-hand side. Okay, so this is an electrical field over a two-dimensional domain. It's to be modelled using this equation. And f of xy is simply x plus y. The domain, in both the x and y directions, goes from 0 to 1. So we've got like a square domain. And it is discretized using 4 nodes in the x and y directions. Okay, so here we have our domain. This is 0 to 1. And we've got 4 nodes in the x direction, 4 nodes in the y direction. Dirichlet boundary conditions provide the values for the nodes on the boundaries, and you can see them in that diagram here. So in total, we got 4 computational nodes. Those are what we're solving for. Okay, first thing we need to do is to derive a finite difference scheme. Now, I'm going to use the second order finite difference scheme to do this. Okay. Right, so we start off with our PDE. Okay, so that's our PDE, and instead of f of x, y, I've just bunged x plus y straight into it. And now, first thing we do is, in general, with finite difference methods, is we replace the derivatives with our finite difference approximation. Okay, so okay, so that's the second order symmetric difference of a second order derivative. Yeah, I mean, you might notice my handwriting gets a little bit sort of vague around these sort of subscripts, so make sure yours is neat. So sometimes I put a comma in between the I and J, sometimes I don't. So don't think there's any sort of meaning in that. It's just me being lazy. Okay, and we do the same for the y derivative. So this time the I stays the same, and it's a J that we change. the y direction there. Okay, so in the y direction there. And on the right-hand side, x plus y. Now x is going to have all different, we're going to have different coordinates for x. So we're going to have xi, that's going to be the coordinate of our current node, the x coordinate of our current node, and yj is the y coordinate of our current node. Is rearrange that, and I want ij to be the subject. First thing I tend to do is when I've got fractions is I multiply by the denominators to get rid of any fractions. So if I multiply by delta x squared and delta y squared, hopefully you'll be able to do this as well. Sorry about my left-handedness. We have delta x squared, delta y squared. Sorry about being left-handed. My dad was left-handed, and when he was at school, they, whenever he used his left hand, they caned him on the hand, stopped him from using it. He said that's why he stopped having why it prevented him having a pro cricket career, but I don't think he would have had one. Just don't be left-handed, kids. Anybody play guitar? Are you left-handed playing guitar? So, guitars cost twice as much as you're left-handed, so if you're going to learn guitar, do it right-handed. Okay, so what we're doing, we're making uij the subject. Okay, well, we can take out common factors. Okay, so what I have here is I have minus 2uij. That will be delta x squared plus delta y squared. Okay, so what I've done here is I've taken out, well, there's 2uij, and there's 2uij. Okay, so take it out as a common factor. I've left a subtraction. I'll leave that subtraction in. Okay. And on the other side, so we have minus delta y squared u I minus j plus I plus j minus delta x squared, and the same but in the y direction. And that's plus delta x. It's pretty much straightforward algebra. I'm not doing anything sort of special here. Okay, all I'm going to do now is just divide throughout by minus 2 times delta x squared plus delta y squared. Okay, so yes, I'm going to divide throughout by minus 2 times this bracket. So we end up with delta y squared plus u plus 1j delta x squared be all over squared plus y squared. Notice at the moment I've just left delta x squared, delta y squared in there, but I know what they are for this particular problem. Well, I can calculate it. I don't know what they are yet, but I can calculate it. Okay, so on the left-hand side, I've got what is the value of the node I'm trying to calculate, and on the right-hand side, I've got expressions involving neighbouring nodes, and I've also got this. This is the f of xy here. But if I have a look at the let's just bring it down slightly. Okay, this had a value of 0. Well, the x was 0 here, the x was 1 here. So what's our spatial step in the x direction? How many steps have I got? Are you ready? How many gaps have I got between those here? 3. Okay, and the length of the domain is 1, so my step is going to be 1/3. And it's also the same in the y direction. So if that step is 1/3, so we've got delta x squared is going to be 1/9. And that's going to be equal to delta y squared. Therefore, okay, I'm going to have 1/9 times all of that. Plus 1/9 times y difference. 1/9 times 1/9 is 1/81. All over 1/9 plus 1/9 is going to be 2/9 times 2 is going to be 4/9. Always run out of space for myself. Again, there are too many fractions to my liking there, so I'm going to simplify it. If I multiply both top and bottom by 9, I'll get rid of a lot of those. Okay, so that's what I'm going to do now. If I multiply top and bottom by 9, on the bottom, 4/9 multiplied by 9 is just going to be 4. So I'm going to write that, instead of dividing over 4, I'm going to multiply by 1/4. Okay. I'm a bit bored of writing i's and j's, so I'm going to just go to the compass notation. Is that all right? Okay, so u north plus u east plus u south plus u west. Okay, because that's multiplied by 9, that just becomes 1, and so does that. 1/81 times 9 is going to be 1/9. 1/9 times x plus y. Okay, and that's our finite difference scheme. Sorry about changing to that compass notation, but I'm just getting bored of writing all i's and j's. Okay, so that's our finite difference scheme. That will give us the value of uij, or I should say uo. That's the original value. Okay, that will give us this value based upon the values of its neighbouring nodes plus in there with that on the right-hand side of Poisson's equation. Okay, so that was derive a second-order finite difference scheme. In part 2, you write out the linear system as a matrix equation. So taking this scheme here, I'm going to write this out. I want to write it out as a matrix equation. Now we don't, as I said before, we don't use that to solve it. I just want to get you, it's important for you to sort of really understand what's going on. Okay, am I able to turn over?
That's okay.
No. Okay. I've just written the scheme at the top just to sort of remind myself rather than having to flick back and forward through those pages. Right, so now what I have, I say I'm not going to have to flick back and forward, but for each one of these nodes, I'm going to write down what my scheme is. Okay, so for node U11, going to be 1/4 times the node above, which is U12, plus the node to the right, which is U21, plus, and we've got 1 plus 2 here. Okay, node to the bottom, node to the left. And then that's minus 1/9 times the x-coordinate plus the y-coordinate. Okay, so what's the x-coordinate of U11? Anybody know? Okay. So what's the x-coordinate of that node? Anyone? The domain is from 0 to 1, so what's the x-coordinate of that node? 0. So what's the x-coordinate of that node? What's the step? 1/3. So that's going to be 0, 1/3, 2/3, 1. Okay? So the x-coordinate of that node is 1/3, and the y-coordinate of that node is also 1/3. So we've got minus 1/9 times 2/3. This is where I reach for the calculator. So just going to calculate 1 plus 2 minus 1/9 times 2/3. U12, U21 plus, and that is 79/27. Okay, if we move across to U21, we've got the node to the top plus the right-hand boundary, which is 1, plus the bottom boundary, which is also 1, minus 1/9 times. Okay, so what's the x-coordinate of the node U21? What was the x-coordinate of this node? What was the x-coordinate of that node? One step to the right, the x-coordinate is now 2/3. What's the y-coordinate of U21? Nobody? 1/3, yes. So 2/3 plus 1/3 is 1. So we've got 1/4 U22. Oh, I've missed out the, what have I missed out? I've missed U11 out as well. There's a little, it should have been U11 in there as well. So I got 2 minus 1/9. 17/9. Okay. Now we go up to the second row. So again, so I'm at this node now. So I've got 3 plus U22 plus U11 plus 3. That's minus 1/9 times 1/3 plus 2/3, because the x-coordinate of U12 is 1/3, and the y-coordinate is 2/3. So add them together, get 1. Okay, so that's going to be U22 plus U11 plus, okay, so 3 plus 3 minus 1/9 is 53/9. Finally, okay, so we got 2 plus 1. That's 1/9 times 4/3, because the x-coordinate is 2/3 and the y-coordinate is 2/3, so add them together, you get 4/3. Okay, so we now have 1/4 u21 plus u12 plus 2 plus 1 minus 1/9 times 4 over 3. 77 over 27. Okay, so this is just for this domain in this discretization. So we've got 4 equations. Okay, what I'm now going to do is I'm going to rearrange these equations so that all the unknown u values are on the left. So the first one, I multiply by 4 to start with. I'm going to have 4 times u11. Okay, by multiplying by 4, and then I have to subtract u12 and u21. That'll equal 79 over 27. So can you see where that comes from? That's just this one. Multiply both sides by 4. Take all the u's over to the other side. You leave the constant on the, well, the known values on the right. Do the same with this one. So here, I'm going to multiply throughout by 4. So I'm going to have 4 times u21. And then I'm going to subtract u22 and u11. I'm going to write u11 first. So it's like nicely underneath that one there. Plus 4 u21. And then it's going to be minus u22. 17 over 9. Okay, and I'm going to keep going like that. So I should really label these. So 1 gives, 2 gives. Okay, 3. Doing exactly the same. Okay, so I'm going to have minus u11 plus 4 u12 minus u22 equals 53 over 9. And finally, minus u21 minus u12 plus 4 u22 is 77 over 27. Okay, so this is quite a common way in which we formulate systems. We put all the knowns on one side and unknowns on the other. And then write that as a matrix equation. So I'm going to have a coefficient matrix times by some vector of unknowns equals my right-hand side vector. So my vector of unknowns, if I go row by column order, that means I'm going across before I go up. U11, U21, U12, U22. Okay, on the right-hand side, I'm going to have my vector of known values. And in the coefficient matrix, so I'm going to write down each equation now. The first equation is 4 lots of U11 minus 1 lot of U21 minus 1 lot of U12, and I don't have any U22. Okay, the second one, I've got minus 1 of U11 plus 4 of U21. I don't have any U12s here, so be careful here. So I don't have any of those. I've got minus 1 U22. I keep going, you'll notice there's a pattern. And that's the linear system. You can solve that using, if you want, this one's quite small, so you can easily solve it using Gaussian elimination or any other linear solution method. Gaussian elimination wouldn't be very good. You require an iterative indirect method. Does that make sense? You see where that comes from? So if I sort of backtrack a bit, we derived this using our finite difference approximations by replacing the derivatives with finite difference approximations. For each node, you can then calculate a linear equation in terms of its neighbours, do a bit of rearranging, and we get down to this linear system here. Okay, what we're going to end up doing is just this last step is that can be solved, but we're not going to do it in the traditional sense. We're going to be doing it with Jacobi method. So our Jacobi method okay, so remember the superscript k plus 1 means that's our improved estimate. Is equal to 1/4 times the node above, but from the kth guess, or kth estimate, that's the node to the right, the node underneath, that's the node to the left. And now there's also minus 19 times xi plus yj. Okay, so that's our Jacobi method for this. Okay. Very easy to convert from our finite difference scheme to an iterative Jacobi method. And I'm going to fill out, well, we're going to fill out this table here. So we're going to give the starting values of zeros. Okay, a bit of calculator work. Okay, so to start with, just turn back here. Okay, so the nodes to the north and to the east both have initial values of zeros. We have this 1 here and a 2 here. Those are only non-zeros. That's 0, 0, plus 1, plus 2. So that's 3 minus 1/9 times 2/3. Because x is a third, y is a third. Okay. And multiply that by 4. And that's our first value, 0.73148. Okay. The next one is 1 plus 1 minus a 9th. Okay. The reason it was 1 plus 1 is because those are the boundary to the right and to the bottom. Minus 1/9 times x plus y. Well, x for this node here is 2/3, y is 1/3. So 2/3 plus 1/3 is 1. So it's just 1/9. And that's 0.47 and about 42. Okay, now if we go up 1, the boundaries are 3 plus 3 minus 1/9. That's 1.472. Okay, so that was the upper boundary, 3. Left boundary is also 3, minus 1/9 because our x was a third and our y was 2/3. Finally, U22. Again, the boundary is 2 and 1. So that's 2 plus 1 minus 1/9. In this case, the x and y coordinates are 2/3, both of them. So add them together, you get 4/3. So 2 plus 1 minus 1/9 times 4/3. 71296. Okay, so that's our first iteration done. Should calculate the error. Because those are zeros, all we have to do is square each of those and add them together and square root them. Okay, so 0.731481 squared, and do the same for all the others. Quite right. Ah, in square level. Okay. 3055. Okay. Next step. Right, so we go back to this one now. So this, we got an error of 1.853. That's pretty rubbish. We're not happy with this error. So what we're going to do is we're going to try and improve that. So in this case, we're using all of these values. Okay, so we have a quarter times, well, the sum of the boundary nodes is 3, plus the node to the right, which is 0.472222, 1.47222. Oh. And minus 1/9 times 2/3. That's 1.217592. Anybody getting a bit bored yet? I was hoping you'd say yes. Right, we don't do that. That's madness to keep doing that way. Okay. Yeah, I mean, I sort of did that exercise with a bit sort of to show you, but yeah, we're not going to do it that way. Is it? Let me come in. Right, let's bring out our old friend Excel. Hello. What's happening here? Now, give me a sec. I don't know what's going on with the computer. Hello. Ah. Yeah, give me a sec. I don't know what's going on here at all. Go away. Where are all my applications? Well, I did want to show you Excel, but the computer seems to not want to play. Oh, I'm just going to stop that. Sorry about that. Give me a sec. No, it doesn't like anything. I've got spinning beach ball of death. Is it still? Okay, I did want to show you this, but okay, I'll come back to that. Wait. Hopefully it will start to play nicely. Right, so yeah, I'm going to come back to that. In the labs last week, I handed out a sort of a guide to writing maths papers. Anybody not got this? Have you? I've got a few spares here. How many do I need to split? Yeah. Anybody else need one? Okay. You're going to start to realise with the work you do this year, especially with your project and in this unit, is we're going to expect you to start to be able to communicate what you know and what work you've done in a manner which can be easily understood by somebody else. Okay, so what that doesn't mean is you say, okay, question 1 is the answer, question 2 is the answer. So that doesn't sort of give any information about what method you've used. So in the lab sheets, I think at the bottom of each lab sheet, it says write up your sort of work you've done in the form of a short report. Now these reports are short. They're 3 pages long. They shouldn't take hours and hours. I expect they may take between 1 and 2 hours for you to write. Any more than that, you'll probably put too much effort into it. Okay, it's all about giving you practice at writing these papers. I'm not expecting you, and you shouldn't expect to get a perfect one done first time, first attempt. It just doesn't happen. So that's what, well, I'm expecting you to do for lab sheet 2, is actually write up, if I just actually find lab sheet 2, what I mean by that is, right at the bottom, write a short report, no more than 3 pages in length, that presents the solutions to tasks 3 to 8. By that, I mean, don't do questions 1 and 2, because there's far too much typing involved and all that algebra. So it's just the calculation of the derivative of cos x using the first, second, and fourth order difference. Also the errors, and produce a log-log plot of the errors. Hopefully you've probably done all that by now, hopefully. So now, if you are sort of thinking about writing up, this is a sort of short, very, very short guide, by the way. It's kind of very, very condensed. There's a lot more out there if you want to sort of look at mathematical writing. But what is a paper? Well, when we do a bit of work, we do, well, when I say we, I mean mathematicians or researchers, we do a bit of work. We write our findings up in the form of a paper. Now, these aren't massive, long documents. They're normally between about 10 and 20 pages in length. Each journal, and the editors of the journal decide whether what you've done, what your work, your research is good enough to be included in their journal. And they do that by sending it off to peers. So they'll say, if I do some work, they'll send it off to somebody at another university or another researcher somewhere. And they'll read it and they'll say, yes, this is good, or no, that John bloke doesn't know what he's talking about. So, you know, you get a bit of feedback. If everything's good, gets published in the journal, and that's what we call peer review. Okay, so when you read things when you read journal papers, the author's peers have said, yes, that's good enough, that's a good piece of work. Okay. So what I want you to do in your lab sheets is actually do some reports. Okay. Written English should be fairly formal. Okay, it should be done in the third person. Okay, avoid any slang terms, any sort of avoid contractions. So can't is a contraction of cannot, so it's always better to use cannot. Avoid using I and we. Okay, it is a bit of a weird way of writing, but you get used to it. Okay, so the written English should be formal, free of spelling and grammar errors, things like that. Now the structure to a paper. Academic papers have this following structure. All papers start with an abstract. Now, in an abstract, an abstract is just about a paragraph which essentially readers use to determine whether it's worth their while actually reading the paper or not. It's kind of like a synopsis of the paper. So the abstract should reflect the purpose of the paper, why is it being done, what you've done, in very, very general terms, what methods you've used, and some main conclusions. Okay, so for example, for lab sheet 2, you can say 3 finite difference approximations were used to approximate the derivative of a cosine function, and their errors compared. It was found that the fourth order approximation was more accurate than the second and first order, for example. Okay, so that's your abstract. Introduction, this is sort of like the what, why, how, where, and when. Okay, so introduction should clearly state what the paper is about. Okay, the rationale for why are you doing this? What's the motivation? And perhaps more importantly, what previous work has been done on the area. So the literature review, for example, if those of you doing the projects. Okay, so that's what that's all about. Then you get the methodology, the middle bit. Okay, methodology, this is where you explain what method you use. So for lab sheet 2, you're saying, okay, we're using the first order, a second order, and a fourth order difference. So explain what they are. You don't have to go into detail. If the work's already been done elsewhere, you can cite the work. So if you find a nice textbook with those, finite differences in, cite it. It's better to cite a textbook than lecture notes. The reason being is if you were to give your paper to somebody outside of this university, they don't have access to your lecture notes. It's always best to cite published works. Methodology should explain what you're doing in very clear and concise terms. Don't waffle. Sort of scientific writing is all about being direct and to the point. Present your results, graphs, tables, etc., and always comment on your results. There's no point putting a graph up without any sort of explanation or comment on it. And then you've got conclusions. Now the conclusions, sometimes you'll feel like you're repeating yourself. That's natural. In the conclusions, you'll be done, so you will be repeating yourself a little bit. And what conclusions were made. Now this is important. No new arguments or data should appear in a conclusion. So there should be nothing sort of new revealed to the reader. Okay. By that stage in the paper, they should have seen everything, all your results and things like that. You can't suddenly, oh, here's another result in the conclusions. Okay. Conclusion section should include recommended actions and also maybe areas for further work. Okay. All conclusion sections should finish with that. List of references at the bottom, Harvard referencing, you've all seen how to do that. If you haven't, there's a very good referencing guide on the MME website. And appendices or appendix at the bottom, any unnecessary sort of things which are a bit too boring to be put in the main section of your paper should go to the appendices. So maybe a reader shouldn't really need to see that, but if they're interested, they can. Is that sort of clear? Have you seen those sort of sections before? Okay, and then formatting. Title should be slightly larger font, include the title, which normally titles are about a short sentence. Okay, so titles are not to papers are normally a short sentence. Include the author name, i.e. your name, the date, your affiliate organisation, which in this case will be Manchester Metropolitan University. Sections and subsections, they should be labelled and numbered. So that formatting is a section, so it's got the number 4. This is a subsection, so it's numbered 4 point something. Now for your lab sheets, I expect you probably have an introduction section, numerical model, results, conclusions. And, so that's probably the main sort of sections. You don't need any more than that. All mathematics should be properly typeset. If you're using Word, get used to using the equation editor. If you're using LaTeX, get used to using the math mode in LaTeX typeset. Variables are normally in italics, so you can see like that V there, that's in italics. Things like vectors tend to be in bold and unitalicized. Figures, nice and clear, should be centered on the page. And notice we have a caption underneath, so this caption. Figure, then the number, so this is the first figure in the paper, so it's figure 1, then the caption. Now a figure caption should tell the reader what they need to know about this without having to refer to the text. Okay, so model a top hat function using the last one drop scheme. And finally, tables as well. Okay, table captions normally go on the top for some reason. And referencing, I put a link to the referencing guide there, which is really, I mean, that referencing guide is good. One of my project students had to reference a computer game. I thought, how do we do that? And on that, you can see the referencing. They got sections for how to reference computer games, textbooks, newspapers, videos, movies, etc. And this is a handy thing I found. Well, I kind of nicked it, but I have cited it, so it doesn't count as plagiarism. Okay, once you've written something, okay, just do this little checklist. Just sort of check over your work. You know, does it answer the purpose stated in the brief? Does it answer the needs of the reader, etc.? So that's a little checklist which you can sort of, by going through that checklist, you can help improve your own mark before you hand it in. So don't make any silly mistakes. Right, any questions about the lab sheet? No. You look like you've got 1,000-yard stare. Okay. Fair enough. I think I know what you're thinking. Any questions regarding what we looked at today? Is it fairly easy? Is it hard? Is there something you didn't? Is it too easy? Sorry? Okay. I won't go any harder then. I'll keep it at that level. Yeah. Right. I'll see you all in the labs this week. There is a sign-in sheet going round, so put your name on it. And I'll see you in the labs.
Give you a message.